Ohayo gozaimasu, part 3. Last time, we studied the heat equation with an unknown generation term. And we used data to develop a model guided by physics. Today, we're going to up the ante to nonlinear dynamics. Suppose you're an experimentalist and spent several years developing an amazing system where now you're able to measure the concentration of some chemical species as a function of position and time. For simplicity, let's suppose you have a 1D example where you have some position x and time t. And you have a measurement across your domain of positive x going from x equal to 0 to the domain size L, which is set to 1 for convenience. Now, in this system that you've developed, it follows some kind of diffusion reaction equation, or you at least think it follows a diffusion reaction equation. And that diffusion reaction equation looks like the following. This is a 1D heat equation with some source, which in this case is a chemical reaction. Unfortunately, like many situations, you don't know the precise rate law. So you know that there's some kind of chemical reaction happening inside your system, but you have no idea what the rate law looks like. So you have some arbitrary function that I've denoted as R, so that's the rate law R, some unknown function of the concentration C. So you're measuring some reactants, it's doing whatever inside your system. All you see are the outputs of your concentration as a function of position x and time, and presumably it has some underlying dynamics, which could be nonlinear, that's governed by some function R of your concentration C. Now, if you think back to the previous video with part 2, what we had instead of this function R of C was the following. In the previous video, we considered the heat equation with some unknown source, just like now, except we modeled the unknown source as some function of position x and time. Now, there's an important and key difference between what I've wrote down today, R as some function of C, and what we wrote down last time, F as some function of your independent variables x and t. And one key difference is the fact that here, your function depends on the independent variables x and time. In contrast, what we have today is some arbitrary function of the function you want, which is the concentration. Therefore, this function of C is dependent upon your dependent variable of concentration. Of course, C also depends on your independent variables of x and time, but you want to find the functional dependence on your concentration. Now, there's really many differences, but there's two key differences between a model that has a function as a function of your dependent variables versus one that is only a function of your independent variables. Let's write those down. Now, the first major obvious difference between what we wrote down today, R as some function of C, and some other function F as a function of x and time, is that when what we considered last time of f as a function of position and time, the equation, the partial differential equation, is a linear PDE, which means that all the linear techniques that we all know how to use applies directly through. So we could use spectral methods, separation of variables, linear superposition. All of those techniques fall right through. So we can assume some expansion as a function of basis sets. You can find your coefficients or your weights using linear approaches. Now what we have today is some function of C. So this R as some function of C, in general, could be any arbitrary function. It could be a nonlinear function. In fact, it often is a nonlinear function of C. Therefore, this PDE is now a nonlinear partial differential equation, which usually is really bad news because you can't use all the linear techniques that we solve and we learn in class. All these techniques like separation of variables, linear superpositions, now no longer can be applied in general to nonlinear PDEs. In fact, I teach an entire course to my Stanford engineering undergraduates on applied mathematics, and I go through an entire 10-week course on linear methods of solving ODEs and PDEs. Unfortunately, all of that essentially cannot be applied anymore because we have a nonlinear PDEs, and we have very, very few, basically zero analytical techniques to solve partial differential equations robustly. So that's one key, obvious, game-changing difference between what I wrote down today and what I wrote down last time. So in my undergraduate class, I have a little tree diagram that says you have a PDE or an ODE. The first question, or one of the first questions you should ask is the equation linear or nonlinear? If it's linear, you have some hope. You might be able to play around with it, play a lot of techniques from linearity, like superposition, separation of variables. There's a lot of techniques you can apply for linear equations. There's a whole textbook, hosts of textbooks on solving linear PDEs and ODEs. And then on the nonlinear side, I draw a humongous upside down frowny face because it's just, you can't do much with nonlinear PDEs. So that's one major difference. And that means that this equation is going to be way harder to solve. Now, the second key difference between what I wrote down last time, some arbitrary function of position and time, versus a function of your dependent variable. The reason why we might want to model it as a function of a dependent variable instead is that it improves interpretability. What we did last time was some function of your independent variables. I said we had some material, you had some wire, coil running through it, it's dissipating heat. As you send in electricity, it's generating heat inside your material, and you wanted to figure out the functional form of that wire coil generation of heat inside your material as a function of position and as a function of time. Now, for certain situations, that's very useful, right? It's useful to know if I go to some position and time, I know exactly what the heat generation is. That's what we considered last time. But in this particular case, we want to actually interpret what the rate law looks like. You want to know how your reactants are being converted over to products. So you ideally want a function of your concentration that gives you more interpretability about your mechanism. You get the mechanism of your reaction pathway if you have a function of your concentration C. It allows you to learn a rate law based purely on your concentration measurements. For example, you might have a bimolecular chemical reaction, some rate constant K times C squared. This would correspond to some kind of mechanism where you have some reactant A that collide, come together, and become products. So you have some chemical species A, two of them coming together and colliding and turning into your products. This would be an irreversible bimolecular chemical reaction. Or you might have some other reaction rate law that might look like this. A nonlinear rate law that looks something like this. You have some rate constant C squared times 1 minus C. Now we're going to cover this example a little bit later on, but this rate law is commonly used in chemical catalysis, ecology, population dynamics and biology, epidemics of spreading also follow this kind of rate law, or people model the epidemic spread like using this kind of rate law. So we'll cover it a little bit later. But now you should see the fact that when you have this kind of expression in your differential equation, it's much more interpretable. You can actually develop mechanisms. In contrast, if all you knew was some function of position time, it doesn't really give you some interpretability of what's happening to the physics, chemistry, biology of your system. All you know is there's some kind of source of your reactants or products at some position in time, but that's not really generalizable. If you can get your rate law, then you can take that rate law to another material and then expect the same chemical reaction. Hopefully, that will be the ideal case. All right, so now I hope you understand the key difference between what we covered last time and this time, which is that now we're trying to find some function of your dependent variable, which could be nonlinear. And if you try to think about plugging C squared or C squared times 1 minus C into this PDE, and if I just asked you to solve this, That would be pretty hard analytically. Pen and paper approaches will not work. You'd have to numerically solve that PDE. What we're trying to do is even harder because we don't even know what this is. You have some unknown function, R as some function of C. You don't know what that is. You could be some crazy nonlinear function. You don't know what it is. All you have access to are measurements from your really cool experimental setup of concentration as some function of position and time. So what you have as a person who wants to develop a model is you have measurements of your concentration spatially and temporally. That's what's given to you. You just worked hard and made those measurements. Let me show you a concrete example of what this might look like by showing you an actual study. So there was a really cool paper by Professor Arthur Prindle about metabolism happening inside bacterial colonies. So here what you're seeing is an image of a bunch of really tiny microscopic bacteria. So each little tiny dot you see right here are about a micron in size. So this whole little bacterial colony is tens of microns or hundreds of microns. And what this study wanted to do was to study the metabolic communication and cooperatism between the bacterial organisms. So they wanted to study the metabolism of one bacteria and how they might communicate and be in sync with their other neighbors. Bacteria is commonly known to exist as a solitary individual creature doing its own thing, just dividing, swimming around, attaching, but actually they're very community-oriented. When they attach onto a surface, they form a structure called a bacterial biofilm, and that's what you're seeing right here. And it turns out that once they form a biofilm, they're very, very community-oriented in the sense that they communicate and interact and cooperate with their neighbors. And so they were trying to study, the authors were trying to study how that communication and cooperatism happens by studying their metabolism. And what they used was a marker, a fluorescent dye that can attach onto a specific ion that the bacteria release out of their body when they undergo a certain metabolic change. So bacteria, this is the inside of the body. When they undergo a certain metabolic state, they release a bunch of potassium ions outside of their body and release it into the bulk solution around them. And there's a dye that will latch on to the potassium outside the body and fluorescently report that. So when it senses a bunch of potassium locally, it will shine and you get a fluorescent reporter. It turns bright when there's a huge concentration of potassium that it locally measures. Let me just show you a video of that phenomenon. So what you're going to see is a long time-lapse movie. You can see the time-lapse right here. This is in minutes. Okay. Now this is over hours. You can see that as the bacteria divide and grow and get bigger and bigger, there's a really cool phenomenon going on where the bacteria are releasing potassium into the extracellular environment in the fluid in a very coordinated, cooperative fashion. You can see they all release at a certain time, and it goes inward, outward, inward, outward, and you see this wave-like propagation happening, which is very strange because bacteria, again, are known to act independently and alone, and they don't really care about other people. Not really. It looks like there's some kind of cooperative mechanism going on. Now you can also track the concentration of the dye very close to the edge, and you can really, again, see this pulse of the metabolic state that's being measured across as a function of distance. And the thing is, through microscopy, this is optical microscopy using fluorescence, you can directly measure the fluorescence intensity of a certain chemical species as a function of position along this colony. And you can also get very, very good temporal resolution. So here's the concentration of some chemical species of potassium reporter as a function of time. Okay, so I just wanted to make this statement a little bit more concrete. What would a measurement of concentration actually look like experimentally? Here's an example. We have some measurement of a concentration of chemical species as a reporter of the metabolic state of an organism. And there is really cool, presumably highly nonlinear dynamics of the chemical concentration that we can resolve spatially and temporally using microscopy. And actually, microscopy is an extremely powerful tool available to a lot of experimentalists where there are lots of data that are generated, and so it's very rich and ripe for data-driven models to be developed. So you can imagine that if you're an experimentalist who developed this really, really cool experimental system, you might want to figure out some kind of mechanism of how they might communicate with each other, or how the metabolic rate goes up and down. And maybe there might be some kind of diffusion reaction system going on. The bacteria are dividing, they're growing, they're communicating with each other. And there's a diffusion of that chemical species along space. Now, I'm not necessarily saying that this diffusion reaction system exactly applies to this system. I'm not really a biologist, so I can't really do the mapping, but it may seem plausible as a biophysics experimentalist making a measurement like this to want to develop a model with some kind of unknown nonlinear dynamics for the chemical reaction happening inside your system. So, this is a realistic situation, and this is the kind of data that a lot of experimentalists are able to collect. So you have really, really good spatial temporal measurements of some chemical species, but you don't know what the underlying dynamics were. So the question is, can you use these measurements to develop a model? That's our goal. So our goal is to develop a model, once again, just like we always have been doing throughout this entire series, develop a model that maps position and time to some chemical concentration, C. Also, we'd also like to develop a rate law, R, as some function of C, because you're a biophysicist and you want to develop a model based on your chemical concentration measurements. Now you can think that this is something that a modern PhD student or researcher would really want to do. And I'm pretty sure there's a lot of you watching this thinking, oh yeah, that's exactly my situation. I just did a bunch of measurements and this is like exactly what I want to do. So that's what I hope that I'll address today. For those of you who are amazing at simulating particle-based simulations or collecting raw measurements from your experiments, and your professor told you, oh, can you just go develop a model real quick? That dreaded, can you just do this real quick? As if it's easy. So it's, as you will find today, it's not as easy as it sounds. And I'm gonna get into, again, a philosophical conversation about what is a model and what I recommend you do as a researcher at this age in today, what you can do. So let's get started. For simplicity, every data set that I'm going to use today as measurements are simulated data sets, just like last time, where I will assume some form of a rate law, solve this PDE, save the concentration data, and just work on the concentration data only, now assuming that I no longer know what rate law produced that data. Those are called simulated data sets. So I'm going to use that today. So there's a couple of different methods that one can take. Let's talk about the first one. The first method I'll introduce today is what I'm going to call the gray box model, where we have some kind of PDE solver and we model the unknown chemical reaction using a neural network. So it's a combination of some known physics based on a diffusion reaction equation, plus we're going to take the term we don't know, which is the rate law, and model that with a neural network. So the architecture diagram will look something like the following. Let's build up this architecture diagram together. Now, the main inputs to this overall model should be position and time. So I have some vector of inputs, position, and another vector of input, time, that goes into this block, and this is going to be a PDE solver. We're going to solve this nonlinear partial differential equation. And at the end of the day, we need to get out concentration as some function of position and time. Now you can notice that we've put in a lot of mathematical structure into this partial differential equation. That's the white box influence in this model. So there's mathematical structure based on your physical intuition that there's some kind of accumulation term and there's some kind of diffusion happening inside your system. Now, what we don't know is this term R of C. We don't know the unknown chemical reaction. It's the rate law. We don't know what that is. And therefore, we're going to do a black box type modeling of this rate law R of C. What we're going to do is take out the concentration that comes out of this block and measure the error, optimize the neural network model, and then feed it back into the PDE solver. What we're going to do is to siphon off the concentration that came out of this PDE solver, minimize the loss of the output, your predicted concentration based on your model that came out, subtracted from your true solution, which is your training data. That's your data set that you want to develop your model on. So that will be your experimental data. That is the true dynamics. You measure the experiments, we have simulated data, we have some true concentration data that we're going to train on. That's C true. You're going to take the mean squared error of that, and you're going to optimize the neural network weights inside this block, which is a black box. We don't know what's going on inside there. All it's going to do is take in concentration based upon a new minimized version of that hopefully will get closer to your real rate law and spit out an R sub C. And we're going to iterate. We're going to have a new R sub C. You're going to solve that PDE again with some assumed form of R sub E based on the neural network. You solve it, it spits out a new concentration. You siphon out the concentration. You compare it with your training data, your true solution. You re-optimize your weights in the neural network. You spit out a new rate law, solve it again, and so on. Back and forth, and you iterate over and over and over. And this part is the training part. You're training your neural network based upon minimizing your concentration data based upon the true concentration. Okay, so now this entire part is the gray box. All right, so what I just boxed in blue is our final gray box model. As promised, we're going to develop a model that maps position and time inputs into this box. And as an output, we have the chemical concentration, C, as some function of position and time. So everything outlined in this box is the thing that converts your inputs to your desired output. All right. So unlike a purely black box where the entire blue box is unknown, that's what you would do if you wanted a pure black box neural network. I showed you that last time in part 2. I'm not even going to attempt it in this case because we already know that's not going to be useful. It's not interpretable, it's not generalizable, it's not transferable. It's just not even worth doing at this stage. So this gray box has a lot of mathematical structure. It has physical intuition and insight built into here. You know that it has a diffusion reaction form with some accumulation. You've put structure into your PDE. You've solved it, but there's a term that we don't really know what it is, and we're going to rely upon a computer to figure that part out by using training data in the form of C true. And we're going to loop over this pink cycle where we have a neural network that will spit out some rate law and then over and over again. And once it's properly trained, hopefully, combined with physics and some black box, we have a gray box where it's partially transparent, partially opaque, and we have inputs coming out to outputs. This is our architecture. Now, like I said in the previous video, part of the creativity as modern day scientists, engineers, researchers, PhD students, postdocs, is to design this block. I mean, this is probably 80% of the work conceptually. Now, of course, there's a lot of details in that 20%. That's pretty painful, which I'll go into details right now by showing you the script. But conceptually, in terms of the overarching approach, this is most of it. Being able to design this block is where most of your creativity must come into place. Now, let's go over to the code because I want to show you how I'm going to script all of this in detail. Now, what you're seeing on the screen right here is a Python script. You can probably tell through all my videos that I'm a big MATLAB person. I think that's just from the generations. I went through a generation where MATLAB was the main tool that I learned in school. But also, I really love MATLAB's visualizations, and their figures and graphs are beautiful. And I think the figures for video and lecturing and educational purposes work very well on MATLAB. And I'm not a big fan of Python's graphics and figures. So I usually use MATLAB for many different reasons. For this case, I'm using Python for reasons that I'll get into shortly. But let's not worry about that so much. Python and MATLAB really aren't that much different. If you're a MATLAB user, you should be able to follow this. And I think most young people use Python now anyway. So in that case, you're probably better than me at looking through this code. But let's just step through the overarching concepts with respect to the block diagram and architecture we just drew. So I'm going to do it in different parts. First, what you're seeing on the screen right here is part one, where we define the neural network. So like I said, we need to figure out the rate law as a black box neural network. We're going to rely upon the computer and the neural network to tell us what the rate law is. So we're just here designing the structure of that neural network block. What I'm showing you here is there's some input. There's one input of the concentration coming in. I've designed it so that there's 2 layers, each with 50 nodes. So there's 50 neurons going into another 50 neurons. And then out comes one output of the rate law, R of C. So like I said, this maps concentration to the rate law, R of C. So you can see here that I've shown you here that there's one input going to 50 nodes going to another 50 nodes going to the output of 1. Okay, so part one is defining the black box neural network. So training. Let's write down the different parts. So what I just showed you on the script is an initialization of your neural network that maps concentration to some rate law, some unknown function as a function of our concentration C. Let's keep going in the script. So now after that, we're going to enter this main workhorse called train on data. Now, train on data is going to take several different inputs. The first input is the true raw data from your experiments. In my case, simulated data sets. The next input right here is the spatial discretization. That will be your X vector. I've called it Z list, X vector of your spatial discretization. dt val is the temporal dt time step. D val is your diffusion coefficient of your chemical species inside your material. Epochs is the number of training cycles that we'll go through. Again, I'll cover where this comes in the block diagram. And lastly, LR is called the learning rate. That's how quickly the neural network will update its weights based on optimization. Again, we'll go through that again shortly. So the first couple of lines is just taking those inputs. I fed in initial data, training data, and I'm just loading that into C data. So C data is our true solution, our true measurements. And we have the spatial discretization of our grid. We have temporal discretization, dt. NT is the total number of time steps in your measurements. And D is our diffusion coefficient. Here, what I'm doing is calling that rate law model, the black box neural network that we defined earlier in step 1. So we're going to call model equal to rate law neural network parenthesis. That says, oh, please load and initialize my neural network for the rate law R of C and call that into the variable model. Okay. And then here, what I'm doing is I'm just initially optimizing that model by giving it randomized weights, because we really don't know what the rate law looks like. So for the first iteration, for the first training cycle, we're just going to give random weights as a guessed for our rate law R sub C. Now, after you've done the initialization of all the vectors, the temporal discretization, now we're going to actually enter our training cycle. So what we're going to do is have an outer for loop that will go through the different training cycles. So epochs is the total number of loops that we want to train the neural network on. What we're going to do here in this first line is to load the initial concentration from our true data as the initial prediction for our modeled concentration. So C pred or C prediction is our model. We want C prediction to be as close as to C data, which is our true data set. What we're going to do is to model the initial time, so that's bracket 0 is t equal to 0. We're going to just load our initial concentration data directly into the first time row of C prediction, because we ultimately want to develop a model that will capture the temporal evolution forward in time. So we're initializing it with essentially the initial condition from our true data set. And we're going to store all of those of different time points in C evolution. This is just for outputting purposes. We're going to save C evolution a little bit later on. All right, so now from the outer loop for a particular training cycle, we have entered the time loop. So there's an inner for loop for time t going from 1 to the total number of time steps inside your training data. We have now entered part 2, our training loop, where we now are going to solve the partial differential equation. So now if we come back up to the board, what we just did in part 1 training is to initialize the architecture of this neural network. And as you saw, we're going to feed this neural network some initial weights. Who knows what the functionality is? There's some initialized weights. And it's going to spit out some form of R of C. It's most likely going to be very, very wrong, especially on the first iteration. Definitely it's going to be very wrong. But there is some now known value for R of C. So now what we need to do is we need to actually solve this partial differential equation. And now we can do that because we know the value of RC numerically that the neural network outputted. So all we should do is just solve this partial differential equation numerically. And that's what we're doing right here. First, what we need to do is calculate the different components. For example, we need to calculate the second derivative of the concentration as a function of position. We need to obtain the Laplacian. So back to the code, what we have here is lap is the Laplacian, which I'm storing as lap, is the C prediction. So that's your modeled C. That's the function you're trying to optimize. That's your model, C prediction. And here we're taking the central finite differencing. So we're just literally approximating the second derivative of the concentration differentiation with respect to x. So we can see here, this is just central finite differencing divided by dz squared. That is just approximating the second derivative using finite differencing. Okay. Now we have the finite differencing approximation for the Laplacian. So we know what that is now. And then here we're going to call the model given some concentration C prediction. That's what we have currently. And boom, R is going to contain the rate law. So back on the board again now, we have now the Laplacian term. We numerically evaluated that by just finite differencing it. We now have this R of C that the neural network outputted. So we have everything on the right-hand side. We know our diffusion coefficient, we know our Laplacian, we know this R. We know everything on the right-hand side. Now all we need to do is time integrate this equation because we have a partial C, partial T on the left-hand side. So all we need to do is integrate this forward in time. we're going to see here is exactly that. So we have here is the predicted concentration profile in the next time step is equal to the current concentration profile at the current time step plus diffusion coefficient times Laplacian plus the rate law times dt. This is just explicit forward Euler integration. Let me just draw that on the board. So part 2 of the training cycle is to just actually solve this partial differential equation. So what we've done here is approximate partial c, partial t as the definition of the derivative, differential in c divided by differential in time. I just multiplied through by delta x, or delta time, dt. And now we have d, the Laplacian, which we've numerically evaluated using finite differencing, and then r of c, which we have from the neural network. Now, of course, this delta c looks like the following. So delta c is simply the concentration for all x of t plus 1. So it's the next time step minus the concentration at the current time step of t. That kind of makes sense, right? Because we're approximating partial c, partial time. And so we're taking the difference of the concentration at now and the next time step. So all we've done here is to put this c at the current time step over onto the right-hand side, and we're solving for c at the next time step. So we're forward integrating the partial differential equation. That's what we're seeing right here. So c pred is now been updated to the next time step. So this is c of t plus 1. This is c at the current time step. So the current time step came from above. It's being added to d times Laplacian plus r times dt. That is forward time integration. And therefore, this now new c prediction contains the next predicted chemical concentration profile. And just by the way, this contains all the spatial points. This is a vector of all the spatial points from position x equal to 0 all the way to L equal to 1. So you have all the spatial discretization in x, and we are solving this over time. So it's a 1 by nx vector. Okay, it's a 1D vector containing all the spatial points. Okay, so now we're going to store that current time steps concentration as a function of position into C evolution because we want to save this for later comparison. And then now we enter part 3 right here, which is calculation of our losses. Because think about it. Now, at this stage, we have a prediction based upon our model and whatever the neural network gave us of the concentration at the next time step. When you begin the loop, you have your initial condition. So initial condition must agree because we initialized it that way. The true data, the predicted data, they agree because we initialized it, so the initial condition are the same. The first time step at time t equals 0 is the same. But the next time step, we have no more guarantee that our model is going to spit out the true data anymore. And it's most likely not because our rate law, R of C, is wrong. Our neural network doesn't know anything yet because the initial training cycle, it spit out a random R of C, and we just multiplied it through, and now we have a predicted concentration profile in X at the next time step, but that's probably going to be very wrong and different from the true data set from your experiments. So now we need to compare the two different quantities and obtain the error so that we can correct this neural network R sub C so that it gets closer to our actual true solution. That's what we're doing in part 3. So we have here is the training loop where we calculate the losses. Now, I've commented out some sections here. The hashtag here is commented out in Python. We're going to come back to that a little bit later, so let's not deal with this part for now. And let's go down to our data loss. So right here, we're going to penalize how wrong we are from the true data set. So what we're going to do is take the C prediction, again, that's the next time step C prediction, compare it with the true data right here, and I'm going to take the deviation of that and square it. So what this is doing is it is taking the error of the predicted concentration from the true concentration obtained from your experiments and squaring that. And that's our definition for the error. I'm taking the mean over all spatial positions. So now you have some kind of scalar quantity of your error. And we're going to add that to this quantity loss data, which I've defined back up here before the inner time for loop as loss data set equal to 0. So it's a scalar quantity. And I'm just going to keep adding to that scalar quantity over all the time loops. So right now it's 0 at the initial t equals 0, but now it's going to have some non-zero quantity because our initial predicted guess in one time step future is no longer going to be exactly spot on, or it's going to be very wrong from our actual true data. So we're going to have some error that gets added to loss data. All right, so let me write that down. Just like that. So we have our error, which is the deviation, the harmonic deviation from your predicted concentration minus the true data set. We're doing right here, right now. I hope you can see this training instructions step by step with the overall block diagram. We're doing this step right now because we just now, after the PDE solver, we have a prediction of C. We siphoned off that data, we measured the harmonic loss, and now it needs to go again back into our neural network, but hopefully we can optimize it so that the neural network would spit out an even better R sub C, and that way this will become minimized over many loops. So let's see where that's implemented. So at this stage, what we're going to do is this is the end of the time loop. So you can see here that we have the inner time loop that goes from line 48 all the way down to the point where we calculate the data loss. So now what we're going to do is we're going to keep doing steps 2 and 3 over and over again over all time steps across our training data. So we start at initial time, we're going to march forward, just keep integrating, going forward in time, and adding up all of our errors. So let's draw what we're doing on the board. So what we're now doing is looping. This is your inner time loop from t goes to 0 all the way to the total number of your time steps, n sub t. So we're going to keep doing this over and over and over again, integrate for the next time step, t plus 1, calculate the error from the real data, keep going over and over and over again from 0 all the way to the end of our training data cycle. All right, so now we've done this step. So we have now a concentration profile, a predicted one as a function of position across all the time in the future. Now we're done with our time loop, and we should, at the end, accumulate all of our errors across all time, compare it, and then re-optimize our neural network. So let's go back to the code again. What we have here is this is the end of the time loop. So if we keep going down, what we have here is first we have is all of the stored concentration profiles, which we're going to put into a matrix called C stack. This is going to be a matrix of the total number of time steps along your rows and the spatial discretization n sub x. So it's a matrix of nt by nx. Now, I'm going to come back to all these commented sections a little bit later, but for now, let's just skip this for the first run, and I'll show you all the different things you can do to the loss. Here, what we're doing is taking our loss, which has been added together across all of our temporal data, and we're going to divide it by the total number of time steps. We're just going to normalize and get the time average data loss. And data loss has already been space averaged. Now it's going to be time and space averaged error. Now, at the very end here, we have this quantity called data loss. I'm just going to throw this loss data into another quantity called the total loss. I'll explain how this can change a little bit later once we start penalizing other different terms. But for now, all we have is the data loss. And here is where the main training happens in part 4. Let's write down what we have here. So what we have here is a very important part of a neural network architecture where you take the error and you do this procedure called gradient descent. Because we're on this super complicated multi-dimensional hyperspace, and we have ridges and minima and slopes everywhere. Think of like the Swiss Alps. That's what I think about. The Swiss Alps, mountains, jagged, going everywhere. And we're in some point across the space. And now we want to ski down the fastest to the minima. So we're going to gradient descent down as fast as possible, down the slope. That's called gradient descent. And then we're going to do a step called back propagation, which will update all of the neural network weights. So going back to the screen, that is what these 3 lines are doing. So first, this command right here, optimizer, period, 0 grad, that basically says, oh, please clear all of my gradients inside my gradient descent. This part, I'm taking the loss data, right? This came from total loss, right? And backward parenthesis is where you're taking gradients of all of your weights inside of the super complicated neural network. This is called auto differentiation, automatic differentiation. And in fact, these lines right here is really the reason why I'm using Python. One of the most remarkable things about what I'm doing here is Python has this ability to do auto differentiation and MATLAB doesn't. So let me just explain what's happening here. What we have is way long time ago. Let me just scroll up a little bit. I hope you don't get seasick when you're watching this. I often get seasick when I watch a video of someone scrolling up quickly. Don't get seasick. Okay, so we have this rate law. Again, this rate law is what we define. That's our neural network initialization. That called the neural network, we put it into the quantity called model. So as soon as you do that, this model starts shouldering on. It carries with it all of the neural network weights and all the parameters. So now model contains all the weights of all the complicated 50 nodes, 2 layers of all the different arrows that go from each neuron to another neuron. All those different weights get carried along to this variable model. And every time model gets used later in a calculation, for example, here, model was called because we needed to take the prediction of the chemical concentration and output a rate law. Now R shoulders on all the neural network weights, 50 nodes, 50 connections, everything, right? It's going to connect all of those weights. And now R is used down here. And so now C prediction gets also passed on the torch of all the different weights and all the different parameters in the neural network. So now this gets passed on. It just keeps going. And when we calculate the total data loss, again, C prediction carried all the weights, and now data loss, lost data, carries all the neural network parameters. Now this just keeps going. It was renamed later as total loss. And so now here, when I do total loss dot backward, magically, Python will calculate all the different gradients for you automatically. It'll auto-differentiate along all those different 50 nodes, 2 layers, all the gradient descents. It'll do that, all that for you. And then the next code right here, optimizer.step, that actually then goes to your neural network, the thing that you initialized earlier, and says, oh, hey, please nudge this weight a little bit closer this way because now you're skiing down this mountain closer to the minima. Oh, take this weight, ski down this way, this way, this way. You're doing that everywhere for all of the connections and all of your nodes. So these 3 lines, there's a lot of stuff happening. And this is the step where your neural network over here on the board is receiving information about the loss. It's calculating all the gradients, and then it says, it feeds in instructions back into your neural network and says, hey, can you please update the weights inside your connection just by a little bit here, there, here, there, here, there. And then boom, hopefully it's done gradient descent and skiing down the right direction such that its new output of R sub C is a little bit more close to the accurate answer. That is why I'm using Python. These 3 lines, a lot of magical things are happening, and these 3 lines don't exist in MATLAB. There's no auto differentiation in MATLAB. If someone from MathWorks is watching, it would be great if you can include automatic differentiation in MATLAB. In any case, it exists in Python, so we're using that here. All right, so at this stage, This is the final part where now it has optimized. We have new weights, and then this loops back all the way up here, all the way up here. And now we're in the outer for loop to a new training cycle. So epoch goes from 1 to the total number of training loops. We just did the first loop just now. Now it's going to be on epoch equal to 2, and it's going to redo the same thing. It's going to reinitialize your new prediction with the initial condition from your true data, and it's going to time step through all of your time from 1 all the way to NT. But at this stage, it has now an updated model. It has a neural network for a new rate law that hopefully is a little bit closer to your real model because it did gradient descent and auto differentiation. And so now you can see how the answer might get closer and closer. So going back to the board again here, we've done this update. Now you're going to solve this PDE again, and you're going to get a new solution, and you're going to repeat this over and over and over again. So what that corresponds to in this instruction set is the following. So at the end of each epoch, each training loop, it's going to adjust the weights of your black box neural network. And it's going to loop back, and you repeat this all over again. And you do this many, 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 many times. And hopefully, after you do it many times, the output will give you a concentration that has minimized and is as close as possible to true data set. And now we have a rate law numerically that hopefully is the true rate law underlying your dynamics. Okay, so that is a summary of this gray box model, what's happening inside the code, and how this structure is actually implemented in gory detail. All right, let's start doing actual concrete examples where we illustrate how all of this fits together. Let's do case 1 as a irreversible biomolecular chemical reaction where we have some species A, 2 of them come together and collide, and there's some rate constant K that turns it into products. So the rate law looks like negative K times C squared. It's negative because the concentration that you measured is being consumed. And it's C squared because it's a bimolecular reaction. You need 2 species, you need a collision for them to react, and therefore require some cooperation, and it's C squared. It's a nonlinear term. So now, if I were to hand this to you, and you had to solve this differential equation with negative KC squared, you can't solve it analytically. It's a nonlinear partial differential equation. It's very hard to solve. And besides, the whole point is you don't know what this is. The reason why I wrote this down is because I want to first generate simulated data sets. I want to practice with toy examples where it's a control. I assume a form of the rate constant and the rate law as a nonlinear quadratic rate law. I will insert this into the partial differential equation, solve the PDE, and save the concentration as a gigantic matrix as a function of time and position, and just save that only. And now that's all I have to work with. I have just an entire gigantic matrix of chemical concentration data, and I no longer know that that data came from this rate law to begin with. Okay, so here I'm just generating the initial simulated data. So let me just show you how I generate that data by going over to the screen. So we're back to MATLAB, which is great for visualization. So first, let me just show you the basics. I'm going to set up this environment where I'm going to call the Python function later. So I'm just going to have a couple of lines that just initializes, oh, please be ready, MATLAB, to call Python, right? Set up the environment and the infrastructure. Now I'm going to import this code that I showed you earlier, autodiff_solver. That's where all the subroutines that I showed you earlier were located. And it's cool. MATLAB allows you to call Python functions, which is really nice. So right here, load simulated data. You see this right here? R of C is equal to negative K times C to the alpha. And we're going to do the case example where the rate constant K is equal to 1, alpha is equal to 2. Okay, so that's the bimolecular irreversible chemical reaction with a rate constant 1, and it's C squared. Now I'm going to use the initial condition of a Gaussian, where for all position x, for 0 time, it's a Gaussian distribution. So it's just going to be peaked at the position x equal to 1/2. Again, the domain is between 0 and 1, and therefore x of 0.5 is exactly halfway along the domain. It's got a width to the Gaussian, which is 100 wide, so it's a Gaussian with width 100. And the amplitude out in front has a prefactor of 1, so it's peaked to a value of 1. So it's 1 at halfway across the domain, and then it just spreads out. That's the initial condition. We're going to use Dirichlet boundary conditions, which is concentrations pinned at 0 on both boundaries, x equal to 0, x equal to 1. L is 1 in our case. Now here I'm just creating a vector of concentrations from 0 to 1, and I'm going to put the rate law right here. So this is equal to negative k times c squared. And this data set right here, this MATLAB data set, contains the solution to the PDE with this assumed rate law. So this is what I told you earlier. This contains a gigantic matrix of concentration data, which is a solution to this PDE that I've done beforehand. I'm not going to show you that. I've solved it numerically. I've solved it, and I've just saved the concentration data only. So if I evaluate this script, what you're first going to see is right here. This is the rate law, R, as some function of concentration, as a function of concentration. So this is just saying, here is our rate law. I'm just literally showing you negative c squared, which is our rate law. As you can see, it's an inverted parabola. It's 0 at 0 concentration because there's no reactant concentration. There's rate law is 0. And then it gets faster and faster with more chemical species present. So if you have a lot of chemical species present, they're colliding into each other a lot, and therefore you're consuming the species very quickly. And it connects them parabolically, or inverse quadratic. Okay, so it just gets faster and faster as c goes to a larger value. So this is the rate law. I've solved the concentration profile in this matrix called data. And that data looks like this. So I'm going to play this as an animation. Here's the data. It contains the chemical concentration as a matrix. I have the spatial discretization and the time, which I've also saved because those are our inputs. You need those. And now I'm going to play this. It's going to be a movie. It's going to be a chemical concentration as a function of the domain from 0 all the way to L of 1. Let me just play that again. So initially, it's going to be a Gaussian, like I said, peaked at x equal to 1/2 with a height of 1. And then it just reacts away and also diffuses. So there's a diffusion reaction going on. Playing that again. Okay. If it was just pure diffusion, you just see that peak go out and flux away at the boundaries. Because there's actually a chemical reaction happening, they're being consumed away from your system. So there's both diffusion and reaction happening at the same time. Now, this is all we have. We just have access to the C. I'll actually show you as proof. So C data, if I go over to their workspace, C data is right there. This is it. This is the whole data set. So this matrix is 2001 time steps by 100 spatial discretizations. So it's 2000 time steps all the way from 0 to time, I think, t equal to 1. And then spatial discretization with 100 points between x of 0 and x of 1. See this? That's stored in the columns all the way to x of 100, and then all the time steps all the way down to the element 2001. So you can see that at the boundary, this is your boundary condition, x equal to L equal to 1. It's 0, right? That's the Dirichlet boundary condition. Over the same on the other side, it's 0 boundary conditions all the way across. If I were to plot this at the initial condition, it looks like this. That's the initial Gaussian distribution. The next row contains the next time step, which still looks like a Gaussian because it's very, very small time discretization, and the Gaussian reacts away. And when I string together all these rows, that's the animation you just saw. So, as proof, this is what you have. The gigantic matrix filled with data of your measurements of chemical concentration. Now, I no longer know that it came from this second order chemical reaction rate law. I don't know this anymore. All I have access to is this right in front of you. This is all we have. Now, let's see if we can take this data, use this architecture of the gray box, and see if we can get a good mapping between position and time to concentration. Plus, also, our second goal is to figure out this form of the rate law. All right, let's dig into it. So this is the training where on MATLAB, I'm going to call the Python script that I showed you earlier. I'm going to feed in the spatial discretization, the temporal discretization based on the data that I just showed you. C data was this gigantic matrix, 2001 by 100 that I just showed you. And here, all I'm doing is converting those matrices and vectors into something that Python can read. So py.numpy, that just converts all the vectors and matrices from MATLAB language to Python. I've included my diffusion coefficient. And here are a couple more inputs of the max number of epochs. So I said earlier, you have to do the training cycles. How many training cycles you do is based on how accurate you want your solution to converge to. So you can see here I've played around with a couple of different values. This is largely trial and error. You're just gonna have to try a different number of iterations and see how it converges, right? This int I32, don't worry about that. That's just an integer bits thing. This chemical just detail, don't worry about it. It's just the numbers inside the parentheses is all that matters. And then LR is the learning rate. That, I didn't explain it earlier, but LR, learning rate, is how aggressively do you want to update your weights. So when you do gradient descent auto differentiation, you skiing down the Swiss Alps, how aggressively do you want to ski down is basically what learning rate is. How much do you advance your neural network weights based upon the gradients in the slope? So you ideally want this number to be large so that you update very quickly and you converge to a good solution as fast as possible. But if you're too large, you might ski over the hill and go over to the next minima, where you don't want to be. You might come back and forth and back and forth. You might be stuck in a local minima, whatever. You might just go too quickly, too aggressively. So there's a sweet spot of being aggressive, but not too aggressive with your learning rate. Again, you're gonna play around with this. You can tell I played around with it. Look at all these different numbers that I played around with. Again, this is trial and error, largely. There are some guidelines, but honestly, it's gonna be largely trial and error. All right, so the final input, again, train on data. Remember that? That's the name of the Python routine. Going back to the Python script over here, all the way up here, that was the name of the Python routine, train on data. It's gonna include these inputs, right, which I've just explained to you, and that's gonna be fed into from MATLAB. So I'm going to call Python train on data. I'm going to call the Python function and look at the inputs. C data is the gigantic 2001 by 100 matrix that I just showed you. The data going in there. This is a true data. X discretization for time step, diffusivity, the max number of your training loop iteration, max epoch, and your learning rate. All right. And out from the train on data comes a couple of things. I didn't show you earlier, but at the end of that Python script, it's going to output a structure, and it's going to contain 4 things. First entry, it's going to contain the neural network weights that map the concentration to the rate law that the neural network ultimately went to at the end of the training cycle. It's going to calculate the overall loss, so that's C minus C true squared. That's the error as a function of time, because I want to know, how well it converged as a function of training loop. The spatial discretization, which we already kind of know, so that was kind of redundant. And then finally, we have the predicted chemical concentration profile, C prediction. That's as a function of time and space, that's the final prediction. And hopefully, this gigantic matrix right here, this entry, is going to look something like the training data over here on the left, this gigantic 2001 by 100 matrix. If they're close together, then it worked pretty well, or it may have worked pretty well. Again, going into a philosophical conversation about modeling later in this video. Okay, so I'm going to evaluate this, and it's going to take some time because it's going to call that Python function, go through all that training. All right. It's not the most interesting watching me just stand there like this with a bored face, waiting for the training cycle to finish. So I'm going to adopt the cooking channel format where here are all the ingredients, and look, here's a finished turkey 30 minutes later. That's what I'm going to do. Ain't nobody got time to wait 15 minutes for the rice-a-roni to cook. I'm just going to show you the finished product right here. All right, let's skip forward to the finished data after this training is done. Okay, cooking is all done, and we have our training loop all finished, and I want to compare the final result. Now, let's look at an animation of the actual true data that's contained here inside of C data. That's the data I showed you earlier of 2001 by 100. That's this gigantic matrix. And I have another matrix called C prediction, which is also 2001 by 100. And this gigantic matrix is the final, hopefully, converged data. That is the model that we developed from this gray box model, doing everything I just explained to you for the first part of this video. This is what the final model predicted at the positions and time of the domain and of your experiment. So let's play this moment of truth. Let's see what it looks like. Play this. Okay, so what I'm showing here is chemical concentration along the y-axis as a function of position along the domain, going from 0 all the way to 1, L of 1. The black curve is the true data set that came from your experiments, and the red dashed line is the gray box neural network, which is what we structured. So let's just play that again because I was talking and I missed it. Okay, pretty good. Pretty good. I mean, the curves are right on top of each other. Okay, let me just play that again. That's pretty impressive. Oh, there's a little bit of deviation. Okay, so, early on, there's a little bit of deviation, and it just spreads out. Okay, at the end, there's also, this is nitpicking, right? But there's a little bit of offset. Yeah, this is nitpicking. I mean, if the model is this good, this is pretty remarkable. A little off, but overall, the concentration profile looks just like the true data. Okay, so now at this stage, we have presumably some gray box model with some trained neural network, which presumably learned the rate law that produced the overall chemical concentration based on the solution to this PDE, neural network, and gray box. Just for confirmation, let's check out the rate law, because remember there's two goals to this project. We have a mapping from position and time to the concentration. That's this plot right here. That's kind of achieved. You can see it's very, very good. And the second goal is to have some kind of mechanistic insight for this rate law R of C. So let's just plot R of C, because remember the Python script spit out the neural network weights, so we can reproduce, put in the concentrations, spit out the neural network of the rate law that it learned after many, many training cycles. And let's see what that looks like, because we know the true answer. We know that the answer must be negative c squared. It must be an inverse parabolic I showed you earlier. So let's see how well this training data on the remember, we trained on the concentration. That's what we trained on. That's what was given to you. That's what you measured as an experimentalist. And now we're going to look at the inner workings of this black box element, which isn't guaranteed to agree. So let's check it out. So this is the rate law. I'm going to evaluate that. Take the Python prediction, R prediction, from our model, and then the true rate law right here, which is the inverse parabolic. So let's just see what it looks like. So what I'm plotting here, this is very interesting, is the rate law as a function of the concentration, as a function of the concentration. I'm plotting this from 0 to 1, and the reason why I'm plotting this from 0 to 1 is because the Gaussian initial condition went from 0 all the way to peak of 1. So it was a mountain, a Gaussian peak, fixed at one height, and then just diffused and reacted inside your domain. That was what the data were. So then we're going to have 0 to 1 in concentration. The black line is the true simulated rate law, negative c squared, that looks like an inverse parabola. And the red dashed line is the gray box neural network. You can see that it's pretty crummy. Now, why is that? So the concentration agreed so well, but it's not, especially near c equal to 1, it's not so good. Why is that? I mean, think about it. Let me just play that animation again, because I think that's very helpful. We have this concentration, okay? And let's put this side by side, because I want to see them next to each other. Let's see if there's a way for me to do that. Put them side by side. Okay, that's pretty good. So side by side. So what you're seeing here is an interesting example where you might be a little bit deceived to think that you have a good rate law estimate, whereas it in reality might be a little different. So inside the training data that you gave it, the concentration spanned from 0 to 1. The Gaussian went up to 1 and then it went all the way down. But then very quickly, the Gaussian went away. And so for the most of the training data, you can see early on it was close to 1, but most of the time of the training, it's spending concentration between 0 and 0.5. I mean, look at all this. All these data are between 0 and 0.5 concentration along the y-axis, right? So that means that most of the data that you fed in for this neural network to train on were concentrations over here between 0 and 0.5. So that's pretty reasonable, because it only got a shot to see the c equal to 1 at the initial condition. At the very, very beginning of this video, it barely saw that c equal to 1 along the y-axis at that point only, at that time point, right? And then quickly it went away. So the gray box, and specifically the neural network, only got a chance to see c equal to 1 for like a single time step. So yeah, you kind of expect the trends over here to not agree so well, because the neural network never got a chance to be trained on. It's kind of like you can't be good at anything you haven't practiced on. But over here, when it's closer to the origin at concentration of 0 to 0.5, it's better. It's still a little crummy, honestly. I think this kink is a little bit concerning, and it just kind of looks weird. But it is better, and I think it's close enough such that it looks like most of the data agree in the concentration realm. Again, you're taking this PD and you're time integrating it, and therefore you can be a little bit off in your rate law and still get by with a roughly good concentration data. So again, gets into the philosophical conversation of just because at the end your concentration agreed doesn't mean that you have the right theory or the right mechanism. I mean, in reality, in the wild out there, you didn't know that it came from an inverse parabola rate law. You don't know. So you don't even have a comparison to make. All you see is your concentration data, which you measured, agrees with whatever your gray box produced. And then your rate law over here, this red dashed line is all you see. You don't know this black line in reality. So this is where you have to be really careful. Just because your concentration agreed doesn't mean your rate law is the correct model or the correct theory. But there are a couple of remedies you can make. And let's go through some of those remedies. And the primary part where you can start playing around with is this loss. Well, actually, there's a lot of things you can play around with. You can change the architecture, you can change various things along this gray box, but there's one point-wise specific thing that you can change. That is this term right here, this loss. Right now, we have only penalized how good your predicted concentration is from the true data set. But there are other things you can penalize based upon our physical understanding and intuition of our system. Let's write those down. All right, let's talk a moment about ways in which we can improve our solution by considering different types of errors and losses. I wrote down here types of loss. This sounds a little bit like a therapy sessions. I'm sorry to hear about your loss. It's not that kind of loss. It's an error. Loss terms, error terms, mean squared error. So we already have one of them, which is called the data loss. I'm just going to put that as 0 because it's already in our model. So this is called data loss. This is saying how close is your actual prediction of concentration from your actual data set from your experiments. You want to drive this error to 0. That's what we've been doing so far. That's why I put a 0 out here because it's already in our model. One other type of loss you can include is a penalty on the actual partial differential equation. Because think about it, we're structuring this gray box where we're imposing this partial differential equation. We're saying that whatever experiment you performed obeys a diffusion reaction equation. So we can take this equation and see how well it's matching this equation's structure. The next one I'm going to call PDE residual. May not be the most accurate name for this type of error, but that's what I'm going to call it. What we have here is we have the partial differential equation, which we have guessed must be the underlying dynamics of our system. I'm going to move over the right-hand side over to the left-hand side, such that we're taking the residual of partial C, partial T, minus the stuff on the right-hand side, d Laplacian plus your rate law. This difference must be driven over to 0 because that's what we imposed. We're taking a PDE and we're setting that equal to 0, right? If we set this over to the left-hand side, the difference of dc dt minus all this stuff, that residual must be equal to 0. Okay? So we're now using not just the information about the raw data set of C true, but we're also putting in there information about the equation. We not only want the data to be accurate, but we want it to follow the differential equation. And there's a small little subtlety that I've included here, which is this time derivative uses the true data set. So you're going to put in your true experimental data. You're going to take time derivatives of that just by taking finite differences of your true. But everything over here on the right-hand side is going to be your predicted concentration. So you're going to use your neural network output's solution to the PDE, that concentration. You're going to take spatial derivatives of that, and you're going to include your rate law predicted by the neural network. So this term is based on your true data set. This term, these two terms are based upon your predicted model. And there's kind of a reason why we're taking that mixed approach, where you're taking some aspect of your true data, some aspects of your predicted data set, subtracting the difference and making that derive to 0. Because you're kind of saying, oh, I'm going to learn a good right-hand side that models the left-hand side of your equation accurately. Now, there are different combinations you can take. This is where you, as an experimentalist, as a theorist, as a modeler, you need to just kind of play around with a couple of different things. For example, you might say, well, I want to include the true time derivative and also the true Laplacian, and then focus my training on the neural network part. You can totally do that. But it doesn't make a lot of sense. Well, first of all, it doesn't make any sense for you to include the true here and then true everywhere because you don't have what the R of C true is. It doesn't make also a lot of sense to put this as your predicted time derivative and also everything here as your predicted time derivative, because now you're just saying, is your solution to the neural network output consistent with the PDE? I don't think that will really help too much because you're not using any information from your training data. The whole point of training is you're using information from your training data to make your solution converge to a better answer. This is clearly doing that because you're comparing your predicted value to the true value. Here, if you took your model time derivative and your model Laplacian and your neural network RC, you're not really comparing it against your actual true training set. That's why we've included here the true data set, its time rate of change. This is saying how quickly is my true data set changing temporally. And I want my Laplacian and neural network to match that and catch up and chase that so that my right-hand side is consistent with my data on the left-hand side. Okay? So I'm going to call that PDE residual. By the way, this is the kind of constraint, it's often called a soft constraint because you're harmonically penalizing this And this harmonic soft constraint is often what's included in physics-informed neural network, PINs. Okay? Physics-informed neural network, PINN. Okay? This is very commonly included as a penalty to that type of approach. Now, there are different types of approaches you can also include, but first, let me just show you in code what this looks like. So going over to the screen, what you have here, we're again back to the Python code because that's where we're including the losses. So here at the very top of the screen, this is the epoch. So this is where your training iteration begins. Here is your inner time loop over the time going from 1 to nt. You solve your PDE, you evaluate the Laplacian, you use the neural network, you add it. Okay. Good, so far so good. We've covered all of that. And earlier we calculated data loss. Here is C minus C data squared. That is the data loss. That was already included in the solution I just showed you. Now the new part is this one, what I've called PDE residual loss. It's the deviation from the PDE. And like I said, we're using true data for the time derivative, but the predicted concentration for the Laplacian, the diffusion term, and the rate law. So here, what we're doing, dc dt, we're literally just taking a differential time step of the true data minus the previous time divided by dt. The PDE residual, which I've just wrote on the board up here, is the data's dc dt minus the right-hand side based on our predicted concentration profile. Again, this lap right here came from up here. We calculated Laplacian from our model. That's our gray box model, the prediction concentration. And that's going to go here and add it to our neural network, which again came from our predicted concentration from our model. The difference of that squared is our residual, PDE error. And I'm going to keep adding that to a loss PDE, keep adding it over the time loop. And down here, we're just going to normalize it by the total number of time steps. And look what I've done here at the end. I've taken the total loss as the data loss, right here, that's the data loss, plus I've added another loss right here called loss PDE times this lambda. So lambda is a weighting. So I've just set this to be 1 and also the weight of the data to be 1. So this data loss penalty has a weight of 1, and this PDE residual loss also has a weight of 1. Now you could change these weights. For example, if you want the data loss to be prioritized, you definitely want the data loss to be minimized. You can set this to be something of a larger number, like 10. So now it's going to be 10 times as aggressive in minimizing the data loss compared to your PDE residual loss. So you can put these weights in front of it and then add together your losses. Okay? So that's another type of loss that you can include inside your total loss. And once again, the total loss gets sent into these 3 magical lines: auto differentiation, gradient descent, update of your neural network. So now what it's doing is it's not only optimizing over the data loss to make sure your final concentration agrees with your true concentration, it's also saying, oh, please also look at the partial differential equation and look at the error of your PDE. And you're going to minimize both of them in just the right balance. So you're giving it another optimization to calculate. And that way you can converge, maybe converge to a better rate law for the neural network. Okay, so let's keep going with other types of losses that one could include in this type of approach. Another term that you can add to your overall loss is the curvature. It penalizes sharp derivatives in space of your concentration. So you can take a second derivative, the Laplacian of your concentration minus the true data set's curvature. And you want the difference of that, again, to be driven to 0. So when might this be useful to include? If you were to have some system where your concentration was rapidly changing as a function of position, for example, if your system produced dynamics so that the concentration looked like this, it's very curvy, right? It's got these sharp curves. And in situations like that, that's a region of high curvature, because you can imagine that this point down here, or these points where it's highly curved, are regions where the second derivative with space is extremely large, because you're changing very quickly as a function of position. right? There are rapid changes to the concentration as you move in position. And a lot of times with neural networks, they struggle to converge to these very sharply curved regions. Because when you're just penalizing the data loss, it doesn't know that it's changing so quickly. And therefore, including a curvature penalty like this could be helpful. So going to the code, I'll just show you where I've included that. So that is this part. So compute Laplacians. Let me uncomment that section. So here what I'm doing is just calculating the Laplacian by using finite differencing. So C stack is the predicted concentration. So I'm taking the finite differencing of that, right, divided by dz squared. And I'm taking the true data, which is contained in this C data set right here. And I'm, again, taking central differencing of each of those true data sets, and that's my true Laplacian. I'm just taking this difference of the predicted Laplacian from the true Laplacian, squaring that, once again, coming down here, commenting that out, and now you can put a weight to that, to some value, and now you include that into your overall total loss right here, and you can add that to your overall loss. Okay? For our particular case, you know, the Gaussian going down, yeah, it's not really curved. So I don't expect this to really help in our convergence. Let's keep going with a different type of loss you can include. Another type of loss that one could include in the error is called a velocity loss. That is taking the time rate of change of your concentration and taking that error from your data set's velocity, that how quickly is your concentration changing as a function of time, that must be driven over to 0. So here's a situation where you might want to include this penalty. Remember that rapidly spreading metabolic rate of the bacterial biofilm that I showed you earlier? There was like a really rapid wave that went across, right? There was a peak. There was some high concentration of potassium in the extracellular environment that quickly traveled like a wave. So that's like a velocity of your concentration. That's telling you how quickly is my concentration moving inside my domain. So if I were to have a measurement of my concentration as a function of position x that was rapidly propagating or changing in time, like a wave, like that, where the arrows indicate the wave, the velocity of the concentration as it changes in time. When you have rapid dynamics, where your velocity of your fronts are very fast, then including this penalty is a really good idea, because what it's doing is it's taking your model's velocity of your time rate of change of your concentration and saying, does it catch up appropriately to the time rate of change of your data, of your true experimental data? You want to make sure it does so that you can capture these rapid dynamics. Okay, so you could also include that. I'm not going to show you on the code of how you include that, but you can imagine how you can include that too. Just take the forward time step of your true data, the forward time step of your model, and then minimize that error and include that into your total loss. Now, there's one final loss that's pretty common that I wanted to talk about as well. The final class that's very common to include in your total loss is a penalty for your boundary conditions. That's something we haven't talked about so much. All I said is that this system had Dirichlet boundary conditions, and you kind of know that from your physical intuition of your system. So then if you know that from your intuition, you might want to, for example, include a Dirichlet boundary condition penalty, where you take your model's predicted concentration, subtract it from your true value at the boundaries. So here I'm just showing as a representative point x equal to 0, which would be your left-hand side. But you can also include it on your right-hand side. Okay, you could include both penalties at x equal to 0 and x equal to L. And you just subtract the difference at those boundary points and make sure those are penalized properly. That's a little bit different from actually penalizing the overall loss across your entire domain, across all time. This is saying, hey, please specifically look at the boundary points and make sure that that is very, very accurate. And you want to drive that to be going to 0. If, for example, you had Neumann boundary conditions, you would just adopt this to a Neumann condition. All right. So if you were having a Neumann boundary condition, as an example, you'd want to take your derivative in space at some boundary of your predicted concentration at x equal to L or x equal to 0, subtract that from your true data's derivative at that value, and you'd want the difference of that to be driven to 0. And that's saying specifically, hey, please make sure that my Neumann boundary condition is satisfied at the boundary conditions. Now, there's an entire zoo of other types of losses that one could include inside this training process. Now, the more losses you include, the more you dilute the training, because now you're making it optimize over so many different things that the computer gets confused. What am I supposed to optimize over? You're telling me to do 5 different things? Oh my gosh, I can't optimize over all of that. And so you have to be, kind of strategic based upon your system and your physical insight about your system to know which terms might be the most important to penalize. So what's very common for physics-informed neural networks, PIN, is to have some aspect of the PDE residual and the boundary condition loss. I think the very early formulations of PINs in the 1990s were penalizing the PDE and penalizing the boundary conditions. But in this modern age, people combine all sorts of different losses that works the best for their particular system based on their physical insight. So based on this, I'm going to try re-evaluating my simple case, well, relatively simple, of this irreversible biomolecular reaction where I have a quadratic concentration, consumption rate, and I'm going to retrain, do the exact same thing. I'm going to run this training. And what I'm going to do is I'm going to do the case where I'm going to penalize my data loss, of course. And I don't really expect my Laplacian to be terribly important. So I'm just going to penalize my PDE loss, the residual, and my data loss. And I'm going to run this, and I'll report back to you what it all looks like. So let's wait a little bit until the training is done for the condition where I've now included this one and this one. Let's see what that looks like next. All right, now the turkey is completely cooked. I've evaluated this gray box for this new loss penalty based on the residual of the PDE and also the data loss. Let's see what that looks like. So first, let's look at the final result, moment of truth, of the concentration as a function of space for different time points. Here it is. The Gaussian that just goes down as a function of time. So it's really, really good. I don't know if you can tell the difference from the earlier case where I only had the data loss, but this PDE residual, I think, made it even better. I mean, it's better. I don't even see a wiggle anymore. I mean, if I zoom in, yeah, that's definitely way more zoomed in than earlier. I think earlier I was at the first or second decimal point. Now we're at the third decimal point, and there's of course going to be a little deviation, but that's like amazing. I mean, if you zoom out, that looks really good. So this is pretty good. It's even better. So clearly, having the PDE loss looks like it's made the solution better. But once again, you might argue, well, earlier it looked pretty good here too. So let's go ahead and look at the actual rate law. So now the neural network learned a rate law. I'm going to look at those weights, plug in those concentrations. Let's evaluate this and see what it looks like. Boom, here it is. So here is the rate as a function of concentration. The black curve is the inverse parabola. This dashed red line is the neural network trained gray box rate. And it is clearly better now. I mean, do you remember the earlier plot? I mean, it was like jagged, it went straight and then went down and heavily deviated close to concentration of 1. In this case, you can really tell that the dashed red line's trying its best to hug around this inverse parabola. And it's trying its best. You can see that it trained, and now it's getting better and better around this inverse parabola. So that's now it must be clear. If you were a little bit skeptical based on the concentration decay and saying, oh, I don't really can see a difference between what you did earlier and what you did now you can see it's pretty compelling that it is noticeably better when you include not just the data loss, but also the PDE residual inside your overall minimization. And again, like I said, it's not going to be good close to concentration of 1 because you didn't feed in much training data sets that included that concentration rate. So that's kind of expected. But I'm actually surprised that it did so well, even at these higher concentrations of 0.8, 0.75 around here, it's still really good. Okay, so we just finished our first example. I think this kind of a nice example using a very simple toy case of just how this gray box architecture works. And now we have everything we wanted. We were given the data set on measurements of your chemical concentration data, a gigantic matrix, 2000 by 100. Our goal number one was to be able to map inputs of position and time and output concentration. That's what we've done. And our second goal was to have some kind of model or some kind of output of the rate law R of C. So you can now imagine that if I were to take this dashed red curve and fit it to a polynomial, I'll probably get a parabola to come out at the end. So now if you take the data from the red dashed line and fit it, you would get some kind of whatever fit you assume. If you think it's a polynomial, then you would include weights in front of the polynomial, now do least squares regression, and try to come up with a rate law after that. I'm going to talk about that kind of fitting in the next video when we talk about sparse regression approaches, which is also a very popular and increasingly powerful technique, especially as our data gets better and better in terms of our measurements. So I'm going to talk about that a little bit later. But for today, this was a good example where I showed you how this all works. Now, I wanted to move on to show you a slightly different example. I think a cooler example of the assumed formula rate law, where it's a little bit more complicated. It's not just an irreversible biomolecular reaction, but let's try a more challenging case. And now you're going to start to see that this is not going to work so well. And then we're going to dive into a philosophical conversation about whether this all is all worth it or not.